So next case study will take up on bolted lines. And the first case we take a very simple problem to understand how to model a bolt and nut connection. Let us take this problem. We have a cylindrical sleeve or a cylindrical member. It's a cylindrical component. See, its area is its cross-section area is available, its Young's modulus is available, and its what is called length is available. That gives us K of the component. Stiffness of the component is available for this. Knowing its area of cross-section, length, and Young's modulus, we get it. Then what we do, we take up a bolt and nut. This is the sharp region. So this is a simple connection, the bolt and nut. This bolt head is rigid and it is butting against this surface. This is treated as a completely rigid member. And the shank region from here to here is elastic. And from here onwards is going into the nut. The nut region, when it is inside, this is assumed to be rigid from here onwards. So the bolt or the shank of the bolt that is in between the faces of the bolt and nut is taken into consideration for the effective length. You say it is effective length. Its Young's modulus is available, its area of cross section, effective area of cross section is available. That gives us the bolt stiffness. Now the thing is, after fitting the bolt and nut snugly, when it says snug fit, what do you mean by snug fit? The gap between the faces of bolt and nut is exactly equal to the length of the cylindrical component. There is a snug fit, there is no gap. At the same time, there is no. Now we tighten it. We tighten the nut by say half turn or quarter turn. Knowing the pitch of the screw for a single lead, for one turn, what happens? The advance is one. So with this we will be knowing delta. So for a given amount of turn, the nut will be advancing by delta. And for this we need to find the stress induced in the cylindrical component and also in the bolt, shank of the bolt. That's the problem. How do you tackle this? These are the normal circumstances problem.
Delta net is equal to delta net is equal to delta mod of bolt plus mod of cylinder.
What of?
Delta mod delta of net
Modulus.
this cylinder portion plus bolt portion.
So cylinder will be in compression, and shank level bolt will be in tension. So the extension of the bolt and compression of the cylinder is equal to delta. The absolute value of compression plus absolute value of extension of the bolt is equal to delta. That's a constraint equation. Now what could be our reference? When we say here this face and this face of the cylinder are in contact, immediately we can say both are at the same location as 0. At that we can say the boundary condition is 0 at this face. Relative to this, the component will be in compression and bolt will be in tension. So at this place both have the same displacement, that's also 0, and here we have different displacements for the component and bolt. So let us say UC is the compression of the displacement of the component and UB is the displacement of the bolt. Can you write down the stiffness matrix? And U1 is 0 for both component as well as bolt. U1 is 0 for both component as well as bolt is 0, and that is the reference. Now once I assemble this, what the stiffness matrix we are going to get? U of the component and U of the bolt. Once I assemble for these 2 degrees of freedom, the first is 0. For the clarity, I will give a little more explanation for this. K1 for the component, K for the component, minus K for the component, minus K for the component, K for the component. This is U1 of component, U2 of the component. Stiffness matrix for the component. And you know, this we have taken as 0 as reference. So this row and this column need not be assembled. So we need to get only Kc. That Kc will be coming here. And this we say, this we call this as U of the component. Suffix 2 we can abandon. Now for the bolt, K for the bolt, minus of K for the bolt, minus of K for the bolt, K for the bolt. And what are the degrees of freedom here? U1 of the bolt and U2 of the bolt. And this is 0. That phase we are taking as reference. And this we say is equal to U of the bolt. When you assemble, these are not going to appear. So this will be appearing here. And this is the assembled stiffness matrix. Right? They are independent. When you fit it snugly, that's what happens. Now once you turn this by half turn or quarter turn for the given initial tightening you have done, then how to tackle this? Once you turn the nut, what happens? There will be a compressive force on the components and a tensile force on the shank. The net compression is equal to the tension on the bolt. If it is possible for us to compute those compressive and tensile forces, then we can directly introduce the force vector here. If it is possible for us to compute those forces, directly we can bring this here. Let us say it is possible, that is a very, very complicated process and we are not interested in going through that route. Then how can we bring it? How can we bring in the constraint condition here? What's the constraint equation here? UC is coming minus UC plus UB is equal to. The delta is the advance of the net over the bolt. That's the constraint equation. Now this constraint equation we can bring into How do you bring this constant equation here? U to B. See, just we can say beta IC plus beta C UC plus beta B UB equal to alpha. This beta is -1, this beta is +1, this alpha is delta. So what's happening here? Kc plus Kp. Here this is minus Kp. This is minus Kp. This is plus Kp. What do you get here? This is minus Kp delta. Here this is B plus Kp delta. After writing this, just check for a while. Check for a while here. Don't go ahead. Just try to understand what is the significance of this negative force and positive force. What is the significance of this? So of the components, the net influence of this assembly is compression on the components negative. In the direction of UC it is negative. In the direction of UB it is positive constant. That you confirm. That's a cautionary note exercise while incorporating this multi-point constraint. We have discussed at length in the previous class about this. Now you solve this, you will be getting UC and UB. And a check here is, after computing this UC and UB, ensure that this condition is met. Whatever the variation, it must be only in the fourth decimal place or beyond for the chosen value of Kp. What is Kp here, tell me? Out of Kc and Kb, which is high? Usually, bolt stiffness is high. So raise Kb by 10 power 4 times, that will give you Kp. Then you get your. See, when you introduce this penalty into the stiffness matrix, if you commit any mistake here, modifying the stiffness matrix, if you commit a mistake, that you can verify by validating the constraint equation. Sometimes, if you formulate this constraint equation wrongly, still you will be getting it verified, but the result may be wrong. Result not, maybe it is going to be wrong. If the constraint equation is wrong, obviously the result will be wrong. That you can verify. Okay? Is this clear? So numericals are there in the handout. You can take the numericals and you can practice it. Though in the class we will be dealing with mostly the theory questions, theory in a brief way. But in the exam we will be tackling with numericals. Be cautious. Unless you practice, your understanding is not correct, not complete, you will not be able to get marks in the exam also. What I test in the examination is your ability to understand the problem and tackling a problem using the concepts learned in the class. Okay. Now we go to the real bolted joint. Think of the design of a bolted joint. Thus we can look into some basics of bolted joints, and I will give it time for you to think of implementing that in FE. Why do we give preload on a bolted joint? Think of a flange connection between two shafts. Flange coupling between two shafts. What is the principle of design? We have two flanges. You take them, put a bolted nut, fit it snugly. Can you leave it? Preload is very, very essential on a bolted joint or a riveted joint. What happens without a preload? For example, if you take any coupling, flange coupling. This I am showing part of the flange coupling. Put these two together, put a bolt or a rivet. When I try to apply a load, what happens? Directly the shank is going to be sheared. There will be shearing. If there is no preload, simply if I turn it, this has to transfer moment. So once you turn it, the bolt will be sheared off within no time. Or the entire moment is transferred as a shear force onto the shank of the bolt, and that will be failing machine. Think of it now, we introduce initial preload on the shank. So these two will be in contact. What kind of stress is there in the components now? When I tighten this with a preload, there will be compression. Right? Now, you experiment with your hands. Just you try this now. Put your hands like this. Without any preload, just they are close together. There is no resistance between them. You can turn it very easily. Freely you can turn them. Once apply moment directly, remove it. If I keep a bolt or in between, directly that will be acting as a shear onto this. Now keep your hands and press them with a little axial force. Press your hands with axial force. Try to give input to one direction. Press a little, no hard pressing. Just press your hands a little hard and try to rotate one hand. Imagine there is a bolt in between. Bolt or rivet is in between. Do you get any load on this? Absolutely zero load on the shank. That's the reason why we give a lot of load on this. Whenever the joint is subjected to shear forces, and the joint is subjected to shear load, a bit of axial force through preloading will nullify the shear force. There will not be any shear force at all. Entire shear will be taken care by friction. And the amount of friction generated is so huge that you can expect with your bare hands. Right? Same thing you try when the friction is less. While taking bath, you experiment this. If your hands are having soap, put a soap, then you press it and try. You can see. If enough friction is not there, then there is a problem. If enough normal reaction is not there, then also there is a slip. So this is one fundamental principle when we design the joint, particularly bolted and riveted joints. Now anyway, if you look at the force in the normal direction, that we will be tackling as a two-dimensional problem that we'll see later. To understand this as a one-dimensional problem, what we do here, imagine we have a component now. Afterwards, these components are subjected to axial force. Only axial force, because we are dealing with the beam element, bar element, we take up only one-dimensional load. So we connect them with a bolt and nut, then we apply an axial load, trying to separate this. What happens to this now? If there is no preload on the bolt, what happens? Whatever the force coming, entire thing will be going as tension in the component and they become loose. There, once the bolt stretches, what happens? The gap between the components will be increasing. Can you allow this to happen? So what do we do? There is no shear load but only axial load. Still, can you just connect them snugly and leave it? So we will be applying preload. Even under the loading conditions, they should be intact, particularly when you look at a leak-proof joint. Joint should be leak-proof. When the joint is going to act as a leak-proof joint, once there is some compression among the components, they will be intact. If the compression is relieved fully, there will be no contact and anything can pass through the gaps. So to design leak-proof joints also, preload is important. If the load is in the shear direction, certainly it is going to oppose it is going to take more shear load, but in the axial direction, it is going to provide the leak-proof joints. Now we need to understand what is the influence of this preload. How do we tackle this as a normal design problem? Then how can we handle these problems with FEA? So without knowing the basic design process, I don't think just by looking at a problem in FEA will help us. So we modify this problem now. You can take a different figure and make it now. I make these two components. Maybe kind of a flange. So this is one component. This we have a two components that are held together. Then we connect them. Okay. First, what we do normally? We're putting a washer. Yes or no?
Yes, sir.
Why do we need to have a washer here?
To distribute the stress.
What's the purpose of a washer here? Both sides, you have to put a washer. When do you go for metallic washers and when do you go for gaskets, soft material? Sometimes we're putting metallic washers, sometimes we're putting soft. When do you go for soft?
Noise.
Huh? So it's a simple diagram I'm giving you. Now what I want to convey here. I don't want to spend much time in giving a beautiful diagram. Just in principle, this is what we do. And after joining, this is subjected to a tensile force P by 2 here and P by 2. So bolted joint in axial So usually when you carry out the analysis for this, so after putting the bolt and nuts snugly, we tighten that by inducing a preload. Then we normally design for a preload. Accordingly, we decide the torque required to tighten the joint. So torch panels are designed and then they will be taken care of the desired preload. We got to a car wheel changing shop, wheel balancing. Anytime if you go, quickly they will be fitting the tires because they have a torque spanner. You know, otherwise manually if you do, we really don't know when it is when we achieve the required tightness or not. So preload is set. Design preload is set. How do we decide this preload first? That's one part that normally we take care of in design. But such preload exists. Then when you try to introduce that into our final FEA model, how to tackle that? That's the second issue. Before that, we need to understand what exactly happens in the basic design of bolt and nuts. On what basis you decide the preload? Once the preload is given, what happens there? That if you understand, I am telling you, conveniently, we can extend that process in a few. Without knowing that basic design principles, if we try to solve this problem with FEA, it becomes a simple procedure or approach of solving a problem. That will not help you. Okay? First, let us stick to the basic design principles here. What happens when we tighten the bolt? When you tighten the bolt, normally what is the region that is affected? In the components, how do we compute the stress in the component? How do you compute the stiffness of the component? Do you think all the component cross section is going to offer stiffness? Experimentally it is identified long back that so the region that is influenced by the tensile force is only limited to a small annulus. A cylindrical region of the component roughly of diameter 3 times the nominal diameter of the bolt. Only the region around 3 times the nominal diameter of the bolt is only will be influenced. Rest of it has no influence. So while computing the stiffness for the component, we take only a cylindrical region with outer diameter 3D and inner diameter D. Inner diameter already is known, but outer diameter 3D, that will be the area of cross section. That gives the stiffness of component 1. Let us use the component 2. When we apply preload, what happens here? When you apply the preload, what happens? Both the components will be compressed. Let us say delta 1 is the compression of the component and delta 2 is the compression of the component 2. Delta C1, delta C2. And also there will be stretch in the bolt. What will be the stretch in the bolt? Will it be function of these two or separate? Independent. That is different. Let us say delta V is the extension. When apply the preload, the components will be compressed and bolt will be stretched. If you know the stiffness of the components and the stiffness of the bolt, maybe. By the way, these two components having some stiffness, they are in series. If two stiffness are in series, can't you get the equivalent stiffness?
Yes.
Remember this, that we'll discuss in a slightly different manner in later class. These two components, when arranged in series, we get the equivalent stiffness. And shall we call this as Kc equivalent? How do you get Kc equivalent by the way? 1 by Kc equivalent is equal to 1 by Kc1 plus 1 by Kc. Equivalent stiffness also can be obtained. Equivalent stiffness of the components and stiffness of the bolt. Then can you represent the preload on a graph? When you apply some preload on the bolt, at a given time, there is a tensile force on the bolt. What happens due to this? The bolt will be, and this, let us say, this is delta V. At the same time, what happens to the components? Will be compressed. See, delta C is the compression of the components. Let us represent like this. This is the original position of the components, and this is compression in the components. What is slope of this? KC equivalent, and slope of this is? This we can say in preload. Look at this. This is P initial load. Only we are just reviewing the basic concepts of design here. After preloading, we give additional load on the joint. P is the additional load on the joint. What happens because of this? If I give extra load on the joint, the P is the additional load on the joint. What happens to the joint now? So bolt will be further stretched. When the bolt is stretched by this amount, what are the components? Components will be relaxed. Yes or no? Originally, under the preload, the bolt is in tension and components in compression, they are in equilibrium. Now there is additional load on the bolt. The bolt will be stretched further and the components will be relaxed by the equal amount. What is the relaxation of the components now? If you look at, this is the relief in the components. Components will be relaxed. Now, what is the total load the joint can take now? Can somebody tell me here? Based on this graph, what is the total load taken by the joint? What is joint load? Huh? Is it this portion? Or is it the total? Huh? Total? From here to here? Then? So this is the total joint. So this is the load. Originally components are in compression, they are relaxed. So originally components are in compression. When the tensile load come on the components, so that will be relaxed. By way of relaxing, they will be taking part of the load. And only the remaining load will be going on to the board. And this is the total joint load. P of the joint. The relief in the component, and this is the additional load on the board. And depending on the strength of the board, we can decide how much we can load here. And depending on the nature of joint, we can decide what is the maximum relaxation we can allow. Components are compressed. Can you allow them to come back? Imagine if you go for a load up to this, what happens? If you go loading up to this point, what happens? Component just they come back to their original state. At this instant of time, if there is a shear load, can the joint take a shear load? Huh? We are analyzing this only for a one-dimensional load. Imagine this system, it has a load transmitting in this direction also. If this component is a part of a flange coupling, if it is a part of flange coupling, the entire load is coming on this. Now tell me, if the total load reaches the state where there is no compression in the components, can you imagine the situation there? Huh? You can think of the joint loads anywhere from here to here. In this case, there is a huge normal reaction. Compression is there. Still there is a compression, there is a normal reaction, there is a huge amount of friction. So there will be huge frictional resistance, and even if there is a shear force, nothing will come onto the shank of the bolt. There will not be shear force on the shank of the bolt. Till now. Once you apply the load till this region, there is no compression on the components. When there is no compression on the components, do you have any normal reaction between the components? If shear comes onto the what happens? Directly it is going on to the shank of the bolt. And maybe their strength in this direction at this moment could be very less. And at the same time, when the joint load reaches this region, here there is no compression among components if in between we have some gases. Say this is the connection between the cover and head of a ICU cylinder. Cylinder and cylinder cover are connected. Once the compression is relieved, both are at their original displacements. Then easily the combustion gases can escape between them. Can you allow that to happen? So for a leak-proof joint, even at the peak of the load, there must be some compression available inside. Okay? So that's the reason why some compression or desired amount of compression must be there. Now this is the problem. For a simple case, we can deal with hand calculations with the desired principles. Now imagine we are doing, say, the cylinder cover of an ICU. We need to analyze all the voltage joints simultaneously. We need to have a model that maybe if you use 4 or 6 bolts on the periphery or on a flange coupling, if you use more number of bolts, then we need to analyze that in 2D or 3D. For that purpose, just let us have a problem in one-dimensional situation. How to model this is our. Let us say Kc1, Kc2 component stiffness values, and let us identify the coordinates here. U1 of the component, here this is U2 of the component 1, this is U1 of the component 2, U2 of the component 2, U1 of the bolt. Let us say this is the transition, this is the region. Let us say this is U2 of the bolt. Now we have identified at element level U1 of the component 1, U2 of the component 1, U1 of the component 2, U2 of the component 2, U1 of the bolt, U2 of the bolt. So we can take 3 elements. What are the elements here? Element 1 is a cylindrical region. This is a cylindrical region. This is the component 1. We can get its area. If the information is not available fully, we can say the inner diameter is available. The outer diameter is 3 times the inner diameter. That is the effective area. There's a proven fact that only up to 3D, the cylindrical region is influenced by the initial load on the board, and away from that, the influence is not felt. So that's why we get the equivalent area as a cylindrical region of D and 3D. Same way, we can take the second component and we can compute its stiffness. The stiffness we indicate as Kc1 and Kc2. Between the two faces of bolt and nut, we can take the cylindrical shank. For that, you can get stiffness Kb. We refer that as Kb. And the corresponding local degrees of freedom identified are U1 and U2 for the component 1, U1 and U2 for component 2, and similarly U1 and U2 for the bolt. Now we need to establish the compatibility conditions. How do we get the compatibility conditions here? Then here, if we take this as a reference, shall we say this is 0? We take the left face as a reference. We can take this as 0. So U1 of the board also can be taken as 0. Both are reference. In between the components, can you see any compatibility here between this? Continuity condition here, both the faces must be having the same displacement, so these two are equal. We can say this is a single coordinate. Let us give the name 1 for this. the displacement at the interface of the two components is same for both. Let us designate with one global displacement. Then what about this now? Any connection between these two? They are independent. One is in compressor side, other concerns they can't be different, they can't be same. So this is U2. Now this is. Now let us write assemble. Let us write assemble. What is assembled is stiffness matrix size U1, U2, what is U1 here? For the component. Second degree of freedom of the component 1. That will be KC1. And for the component 2, this is U1, U2. For U1, U2 we have component 2. K of the component 2 minus K of the component 2 minus K of the component 2 K of the component. So this assembly for the components 1 and 2. Even if you take two components, this is what we get. First, the displacement for the first component is 0. Are you able to follow this? And now if you have any difficulty, you take the individual stiffness matrices along with this local degrees of freedom and identify the 0 displacements, eliminate them, the rest of them are as per our strategy developed earlier. And coming to UB, where are we going to get this? Huh? So U1 of the bolt is 0. No need to assemble the first row and first column of the bolt. Only second degree of the bolt is in the direction of U3. So for U3, we will be getting. Now this is what we have. Then we need to introduce the preloading. Boundary conditions are introduced. Preloading. How we are going to introduce the preloading? First thing, if you know how much is the axial load generated in the board and how much is the compressive load generated in the components when you complete assembly, that load can be directly brought onto the problem as a compression in the direction of U2 and tension in the direction of U3. If that is available, that is right. If that is not available, what is the information available for us? If that is not available, what is the information available? We snugly fit the nut, then we tighten the nut by half a turn or 1 full turn or a fraction of a turn. That means after a snug fit, we tighten this by some amount of delta. We choose the tightening. One way is you give the tightening torque, or you give the preload on the joint as well as components, or simply say after a snug fit, you tighten this by 1 full turn or 1.5 turn. That's the condition. That means the nut will advance on the thread portion by some amount. That is delta. That delta is available. We wish to bring in this condition through this. What's the condition now? What's the condition? The compression of the components and tension of the bolt is equal to. How do we express the compression? It is the constant equation is minus U2 plus U3 is equal to that. Is it so? U2 is the net compression for the components. Right now, what is the compression in the component 1? If I have a difficulty in this equation, what is the compression in the component 1? Huh? So u2 of component, this is u1 minus 0. u1 is going to be minus of u1 minus 0 is the component of the component. What is the compression in the component 2? u1 u2 minus u1. What is u2 minus u1? It is the compression, so that you have to add minus. Then what else we have? Plus tension in the bolt. That is equal to. So this u1 and this u1 will be cancelled. So minus u2 plus u3 is equal to delta is the constant equation. Otherwise u2 is going to be a negative value if you take an absolute minus of u2. That's one. And once I introduce this, what will be the modified stiffness matrix after incorporating this constant equation? 2 minus, so this is plus kp minus kp, which is 200. This is minus kp, this plus kp. Here delta, in the direction of 2 it is minus kp delta, here this is kp, and there's nothing here, so this becomes 0. If nothing is there, that will be simply 0. In this case, again you check what is the influence of the direction of 2. Force we are getting the direction of 2 minus compressive. It is going to be compressive. That you cross check once. Then you solve for u2 and u2. This will give us the condition for preload. Once the preload is over, what next? So for example, now I wish to understand what happens when there is a load P by 2, P by 2 here. In which direction this load is coming? Where that load is coming now? On the components? In the direction of u2 of component 2? In the direction of u2 of 2, that is, in the direction of u2, the additional load can be brought here, 0, P, and on the components in the direction of 2 we are getting here. But due to this constraint equation, we will also get reaction on this. What is the tension the bolt we can generate? External load is only on the components. Out of the part will be going into the components and part will be coming onto the board, and you try to post-process the result. After getting the u2, u3, try to find what are the conditions of equilibrium for the joint. That analysis will help you to understand exactly what part of the load is going into the components by relaxation, what part is coming onto the board. So how to design this effectively, you can understand. Okay. This way you can tackle this. Another possibility I am telling you, later we will discuss a principle called static condensation. In such a case, this 3 by 3 equation solution is going to be somewhat a lengthy process. Do you accept? Somehow if you can get an equation with 2 by 2, don't you think it is comfortable? So you try, after doing this, you try with another simple variation. Here, anyway, we are not worried about the displacement in between at this moment. The displacement interface, we are not worrying. Can we take the combined effect of these two components together with the equivalent stiffness? If we take equivalent stiffness for the components, what happens then? U1 is there. Then if we take the equivalent stiffness of the component, we can write Kc equivalent minus Kc equivalent minus Kc equivalent and Kc equivalent. The equivalent stiffness expression also I have given you here. If it is there, what are the degrees of freedom for the components together? That is U1 of the component 1, which is 0, and this is U3 only now. U3 and U2. This is U2. In between, by bringing this equivalent, we are removing the displacement in between. In such a case, this becomes here Kc equivalent, and here this is 0, 0 Kb, and this will be U2 and U3. This U2 is nothing but the compression of the component, and this is the tension of the component. And now the constraint equation is same constraint equation, minus U3 plus U3 equal to delta. Then if you introduce a penalty, what happens here? Plus Kp, this is minus Kp plus Kp. Here this is minus Kp delta. Here this is plus Kp delta. And solve this. Try both ways and observe the difference what it is. Okay. Now we'll be getting the equivalent stiffness of the components. That is going to simplify the final equation. But now, if I wish to compute the stress in the individual components, what we need to? Again, you have to go back to this. From this equivalent stiffness, knowing stiffness of component 1 and component 2, you need to get the compression of the component 1 and compression of the component 2. Then you have to extract the desired values. But this way, we can reduce these two components into a single equivalent component. Is the concept clear? The same principle we use even in the design also. In the design of bolted joints also, sometimes we introduce the concept of equivalent stiffness of the components. Even it could be two components plus some gasket in between or some washers, anything you can. Is that clear? When I gave this figure, I given these washers, though I have not mentioned, the underlying assumption here is these washers are so rigid, huge stiffness, so they won't deform. We have treated them as perfectly rigid bodies. If I say the washer is not perfectly rigid, it is highly elastic, what happens? Then what happens? We have to take that into account. Its stiffness also must be added in series to the component stiffness. So in such a case, or sometimes if I need to get some more compression during preload, can we introduce a washer that give more compression? Some gasket, if you see, you'll be having a gasket in the form of a ring. Do you have any idea about the cross section of this ring? You see the cross section will be something like this. You'll be having a ring, a compression washer, but its cross section is like this. When it is sitting on one side of the component is here, other side of the component is here, when you press them here, what happens to this? That will be compressed. Still there is a component here. Here, these are the surfaces where the leak-proof joint will be. If there is a fluid on one side of the joint and you want to arrest the passage of fluid from one side to the other side, you can put this kind of washer. So there is going to be. So this washer is known with some name. I'll tell you later. These washers. This is a specific name. I'll tell you later. Sometimes what happens here is, even for a low force also, low loads also, that will give a more compression. In a sense, this combined compression is more. When this compression is more, what happens? The joint load can be more. It can take more time. And even if you think of our IC engines, what happens in IC engines? There is a huge fluctuation of load. During the time of combustion, we are having a high pressure in the cylinder. Then it comes down. There is a huge variation of pressure. So this pressure variation also needs to be absorbed. probably if you have some stiffness, reasonable stiffness in between, which is going to take care of these fluctuations, right? So the fluctuation of stress in the components can be brought down. Only the fluctuation will be there in this washer. Where periodically this washer we can replace and component is protected from fatigue loading. So there are several reasons for using, but how to model them in our systems is important at this point of time. Okay. Whenever you encounter a physical problem, if you understand how it is modeled under normal circumstances, then easily you can extend that through FEA modeling. Many a times people look at, even I've seen people who are doing some projects when they come out with a doubt, immediately they start searching for Google. They'll give you some procedures. But try for a basic design book, you'll be learning so many fundamentals. If you refer the relevant design books, we try to find the physical problem, how it is handled in a normal way. Once you understand that, if you're using a package, you can choose appropriate options, or you can develop your own code when your problem is of a simple geometry. If possible, you can pick some more problems and you can come out with a mini project. Second mind is going to base on mini project. For that, you need to pick your own problem. Choice of problem also is going to have huge weightage. Okay. For today, we will close it here.